Okay, so there were just a few problems I wanted to go over from the progress check. And honestly, of the 5 problems I'm going to do here, I already prepared solutions for 4 of them because I thought that they would be pockets of difficulty for you. First one, question 6. Which of the following is the solution to the given differential equation with the initial condition? Okay, so I'm going to add 2 to both sides. Divide by my 2 minus y. Now I'm going to integrate from here. Okay, the antiderivative, I'm not going to switch colors because it'll mess up the recording. I do need a negative. So this will be the opposite of the ln of the absolute value of 2 minus y, and that's going to equal t plus c. Okay, so at this point you can do one of 2 things. You can solve for c here. So let's do that. Negative ln absolute value of 2 plus 3 equals 0 plus c. Negative ln of 5 equals c. Okay, why did I get a different answer? Never mind, I'm sorry, I did not get a different answer. All right, negative ln absolute value of 2 minus y equals t minus ln of 5. Okay, again, the goal is to get y alone. I'm going to divide everything by -1. So I get ln absolute value of 2 minus y equals negative t plus ln of 5. How do we get rid of the natural log? We raise both sides, and this is where when one student reached out to me, this was the mistake that was made. We raise both sides, e to both sides, so I get, now at this point, I can just get rid of my absolute value bars, and I can get rid of my absolute value bars because I already found c. So this becomes e to the negative t plus ln of 5. That entire expression on the right-hand side is my exponent. All right, manipulating some exponent rules, adding exponents that if I go backwards, that means I was multiplying like bases. 2 minus y, e and ln are inverses, they cancel each other out. So I get 5e to the negative t. Add what, manipulate this equation, and you get y equals 2 minus 5e to the negative t. So lots of people answered D on this problem. Okay, that's one method, okay, from that step. So now my second method that I could take, I could solve for y first. So from that expression, just the integral, I'm going to divide everything by -1, negative t plus c. Remember, the opposite of a number you don't know is still a number you don't know, so I can keep that as plus c. At this point, now I'm going to have e as the base, raise those to the power. So now I get absolute value of 2 minus y equals e to the negative t plus c. Now we can miraculously get rid of the absolute value bars. E to the c power is still a constant that we don't know. So 2 minus c e to the negative t equals y. And at this point, I'll plug in my initial condition. So I get 2 minus c e to the 0 equals -3. Okay, so I get negative c equals -5 and c equals +5. Verifying the exact same equation that I got with the different method. Both are correct. You guys have heard me say this over and over. Whatever you see first, that's the method that I want you to focus on. If you couldn't do either of them, then obviously we'll meet and have a conversation. All right, next one. A lot of you got this wrong, and I think because you sort of just said, you just looked at the answers instead of actually reading the problem. The rate of change of the mass is proportional to the mass of the sample. M represents the mass. So a lot of you picked B, but a lot of you picked A, but the answer is B. Okay, next one. This one was the most challenging one out of all 12. The weight in grams of a population of a bacteria at time t hours is modeled by the function W, the solution to a logistic differential. Selected values of W and its first and second derivatives are shown in the table above. Which of the following statements is true? Okay, so the first thing that I focused on was not the carrying capacity. I looked at the second bit of information. The weight is how many grams per hour when the weight is 10. So when W equals 10, what's the rate of change of the weight? So when W equals 10, what's the rate of change? It's 6. So I automatically know that A or C has to be my answer. So I think I may have mentioned in class, like the way that the table is organized was a little bit challenging. But again, when the weight is 10, why did I pick that? Because that was given in the multiple choice. When the weight is 10, what's the rate of change of the weight? Well, from the table, it's equal to 6. What are my units? Grams per hour. Okay, so I could eliminate that. Next piece of information I looked at the point of inflection. Because I know the point of inflection is when the rate is increasing the most. Okay. So now my point of inflection occurs when the second derivative is 0. And then let me compare these pieces of information. I hope it doesn't pause. Okay. So now my second derivative is equal to 0 when the weight is equal to 35. Okay, well, what's our relationship? The weight, where the point of inflection occurs, is half of the carrying capacity. So where the point of inflection occurs is half of the carrying capacity. So what's the carrying capacity? The carrying capacity has to be 70. So that's what makes it C and not A. Okay. Lastly, question 11, the size of a population is modeled by the given function, satisfies a logistic differential where t is measured in months and my initial value is 50. What is the size of the population at the moment when the population is growing most rapidly? Okay, so hopefully in your work you would have rearranged this, and we talked about we could take out a p over 10. All right, so if we took out p over 10, we'd be left with 1 minus p over 500. Or we could have factored out a p over 5,000, leaving us with 500 minus p. Both of these show us that our carrying capacity is 500. Lots of you picked C. If you got the problem wrong, it's because you picked part C. What's the size of the population at the moment when the population is growing most rapidly? Where does a population grow most rapidly? At A over 2, at my point of inflection. So B was my answer to number 11. All right, and then lastly, I was sort of surprised at this. A lot of you picked A, but let me go back and show you. It looks like I deleted my own annotations, but that's fine. So when I showed you the slope field for a logistic differential, so if there's my horizontal asymptote of y is equal to A. If my initial population is above my carrying capacity, my function will decrease. So if my, oopsie, go away. If my initial population is greater than A, if it starts up here somewhere, then my function has to decrease and approach my carrying capacity. So that's the graph in part A. So A is possible. D is possible because I can see there's a change in concavity. So hopefully you saw from this problem, my carrying capacity is 20, which means that my graph will change concavity when y is equal to 10. So I should, if my graph is going to change concavity, it has to occur when y is equal to 10. So point of inflection at y is equal to 10. Well, if I look at the graph in part B, y never equals 10. So here it means my initial population is somewhere between 10 and 20. In part A, my initial population was greater than 20. It appears from the graph it's actually equal to 30. We can even see it there. On part C, my initial population is somewhere between 0 and 20. C has to be the answer because the initial population is below 10, but no point of inflection occurs. So if your initial population or initial condition occurs below the point of inflection, well then, by definition, you have to have a point of inflection. Okay, so this was that's the information that I need to be able to understand. Then we can start comparing what the initial condition told us. So the answer to question 12 was C. Okay, and that's it from, again, the biggest pockets of incorrect problems that I saw when I went over this.